Hi, everyone. Thank you for joining us today for this webinar. Jason Allen here, the Concrete Pipe Guy. I'm the Technical Resource Engineer for Oldcastle Infrastructure, and I will be presenting today's webinar. Our topic is rigid versus flexible pipe design, a side-by-side comparison. So before we begin, I want to tell you a little bit about myself. I currently live in Utah, and I'm a proud University of Utah graduate with bachelor's and master's degrees in civil engineering. And I've been in the engineering industry for over 20 years now. And when I was 17 years old, I started working as a surveyor and then transitioned into drafting, design, and land development. I then worked in the public sector as a county engineer and public works director. And I've also done consulting engineering work in roadway and drainage design for various Department of Transportation projects, as well as large municipal projects. And now I'm a technical resource engineer for Oldcastle Infrastructure. So some of you may not be familiar with Oldcastle Infrastructure, so I'll quickly share with you some of the solutions that we can provide. I currently live in Utah and spend a majority of my time providing technical resources for design engineers, contractors, and inspectors in the Mountain West area. Now, most people know us by our precast products, mainly reinforced concrete pipe and precast box culverts, but we also provide precast manholes and catch basins. And while this has been our main focus for many years, we have added some really cool new product lines to help meet your needs. Oldcastle recently acquired Torrent Resources, a company out of California that is the industry leader in dry well manufacturing and installation. We've also expanded our stormwater solutions to include storm capture, a total stormwater management system that uses precast sections for underground detention storage. And this system uses the strength of reinforced concrete to provide more area for storage, which drastically reduces the footprint compared to other underground detention systems. We also have multiple stormwater treatment system options like sediment traps or hydrodynamic separators that could fit your specific needs and your stormwater treatment requirements. Our newest addition in the Utah market is gasketed box culvert, and instead of your typical soil-tight mastic joints, we now have the ability to manufacture gasketed box culverts to provide a watertight joint without any additional joint treatment, which saves time and money on installation. Now, as I mentioned before, our presentation today will be a design comparison between rigid and flexible pipes. So let's jump right into the webinar. Okay, I want to start first by giving you a hypothetical situation. All right, now keep in mind, this is strictly hypothetical and in no way resembles any other situation I've had in my career, and any similarities are strictly coincidental. Wink, wink. All right, so here we have some construction drawings, and they call for a 48-inch RCP for this project, for this drain line, okay? Now, the contractor who won the project, he says to you, hey, I want to use 48-inch HDPE because it turns out that his brother-in-law is the plastic pipe sales rep, and there might be some type of benefit and commission on him selling him this pipe. So he wants to help his brother-in-law out. Now, the contractor, he plans to install this pipe the same way as RCP as it shows in the plans. So the plans call out RCP. It shows you how to install it in the plans. But the contractor says, no, I'm going to install HDPE, and I'm going to do it the exact same way as it's shown in the plans for RCP. Okay, so you're the design engineer. Question is, do you approve the change as is? So I want you to think about that for a second while we move on and look at other things. So right now, at the heart of the problem here, we're looking at two different pipe materials, and we have to do some type of assessment here. Now, there's two things we need to keep in mind when we're trying to decide what type of pipe material to use on a project. The first is obviously technical, right? We as engineers, we look at this and we say, all right, what are the technical benefits or the technical things that we need to address and take into account for this project? And the other is obviously financial. Are there financial benefits for one product over another? Is one cheaper? Does one have a better life cycle cost? Those are things that we as engineers need to take into account. So as we're looking at the cost benefit savings, we also have to look at what our risk is associated with these. And so that's kind of what we're going to talk about today. So before we jump into that, we need to establish a baseline here of understanding for different pipe materials and what the purpose of a pipe really is. So the bottom line is that buried pipe must perform two critical functions. The first one is that it has to act as a conduit. So every pipe has a purpose of getting something from point A to point B. Now, in wet utilities like sewer or drainage lines, the goal is to get that runoff or that wastewater from one point, from one inlet box or one manhole to the next one. So it's acting as a conduit to to take water from one point to the next. The other function that it has to perform is that it has to be a structure. Okay, so there are certain loads that are going to be placed upon this pipe, and it has to be able to withstand those loads. So the two functions, conduit and structure. So when we look at the different pipe materials, so concrete pipe is a rigid pipe. Okay, this is a rigid structure that is an engineered product, and it is tested in the plant. When we manufacture a concrete pipe, we go out and we test this pipe to make sure that it meets the minimum load requirements for that class of pipe. So it's an engineered product, and we test it in the plant. Now, flexible pipe can include, this picture here is of a thermoplastic high-density polyethylene or HDPE pipe. Okay, it could also be a corrugated metal pipe. It could be just a standard metal pipe. It could be polypropylene, any plastics, any plastic hybrid like a steel ribbed HDPE pipe or anything like that. Those are flexible pipes, and a flexible pipe is an engineered installation, and it's field tested, or at least it should be. Is it always field tested? Is it always inspected correctly? I don't know. That's a tough call. We hope it is, but I wonder sometimes, based on the installations that I've seen, I'm not so sure that it's always field tested. So concrete pipe or rigid pipe, an engineered product and tested in the plant. Flexible pipe, an engineered installation, and it's supposed to be field tested. So when we look at what loads could be on a pipe, this is a picture that kind of shows a lot of different loads happening at once. So first of all, we're going to have an earth load, or any of that soil that's on top of the pipe. Right. We're also going to have live loads on top of that. So any vehicles or anything that's driving or moving on top of that pipe, that's going to be our live load. We've got construction loads. This is something that sometimes when we design our pipes, whether it's for concrete pipe or for flexible pipe, we're not always taking into account the construction loads. And a lot of times the construction loads can be much higher than any of the live loads that we may see after construction. But we need to keep those in mind as well. Now, surcharge loads is a little bit different. A surcharge load is typically, think of like a water table or a buoyancy, your flotation, the water that's trying to push that up from the bottom. So you've got this surcharge load from a high water table that's maybe trying to lift that pipe up out of the ground. So we've got these different loads that we need to take into account when we're designing any pipe. Okay, so for concrete pipe, we've got our trench here. Okay, we've dug that. So at the bottom of our trench, we're going to have the foundation of our pipe, and then on top of that, we're going to have our bedding. And that can be a few inches thick, depending on how much, what type of installation we're doing. But once we have our bedding set, then we would put our pipe in the trench, and then we put our backfill in up to the spring line. Now, if you notice, the spring line is that midline of the pipe. So if the pipe was flowing half full, the spring line would be right there at the middle of the pipe. And so we would compact and put our bedding material and our backfill material under the haunches, which is that area from the bottom of the pipe up to the spring line, that area under there, the kind of triangle type area. That is considered our haunches. So we would get that in from that material down into there and compact it in there real good. And then we're structurally complete there. Now, I mentioned before we would have some surcharge load coming up on it, whether that's the weight of the pipe is coming. And so you've got some type of load or some weight coming up from the bottom, the pressure and the forces coming up from the bedding and the foundation, reacting to the load or the weight of the pipe on top of it. And then when we backfill, this is our soil load or our dead load that's on top of the pipe. And we would also maybe have some type of live load coming down on it. So you've got to make sure that that pipe is structurally sound and can withstand those loads. And that's what we test in the plant. Okay. Now, flexible pipe's a little bit different. Okay. So with flexible pipe, if we have like that dead load that's coming down on it, and so we've got that reactive force pushing up on the pipe, right? We also have a live load on top of it that's coming over it. That's any of that movement load, like vehicle traffic or anything that's going to be moving on top of that. That's your live load. Now, when we have these loads applied, okay, so we have that surcharge or that reactive load on the bottom and the live load or dead load on top, okay, the pipe is going to tend to deflect towards that fill area. So it's going to squash or deflect a little bit. Okay. Now, a little bit of deflection is okay, right? We know that in most specifications, anything up to 5% deflection is going to be fine. So that's 5% of the total inside diameter is acceptable. But anything above that is, depending on the spec, is either a remove and replace, or you have to have an engineer evaluate it and look at it and make sure it's okay. But small amounts of deflection are okay. And so in order to withstand that deflection, we have to make sure that we have forces on the side holding that into place. And that is where we get the support from the backfill, right? So we have to come in and build that. So when we say it's an engineered installation and it's field tested, this is what we're talking about. We have to make sure as an engineer that we are explaining to the contractor enough to build those backfill. So we have almost support columns on the side of that pipe, so it doesn't allow it to deflect when we load it from the top, or we have a surcharge load from the bottom. So if we're installing that trench and backfilling it correctly and compacting it enough, we should have enough support to keep that pipe from deflecting. That's the idea, and that's the concept here. Okay, so to address this hypothetical situation where we are the design engineer and they're asking us if they can swap out RCP for HDPE, we need to look at a pipe design example. We're going to need to design both pipes to see if they are compatible or comparable and see if we can install them the same way. So our pipe design example is this. We need to perform the necessary design and calculations for a 48-inch reinforced concrete pipe and a 48-inch HDPE pipe with, let's call it 12 feet of cover. So we're going to have 12 feet of cover on top of this thing. So we're going to design these and kind of figure them out and go through what you as the design engineer would have to do to make sure that you are covered and that you're not taking on the liability. So you got to ask yourself, what do I as the design engineer need to show on the plans to make sure that it is installed correctly? Okay. So for concrete pipe, okay, we're gonna look at concrete pipe, and then we'll look at flexible pipe, what we need to put in as the design engineer. These are the things that we need to look at. So first of all, we want to put in a trench detail. Now, the manufacturer of the concrete pipe will provide you with a detail that shows you how it should be installed, and that's based on a national spec that we'll talk about in a moment. Okay. You also need to look at the pipe zone delineation, which we already talked about, is anything from our bedding up to spring line. So any of that backfill material that's compacted under the haunches, that's our pipe zone. So the manufacturer's already told us, this is what our pipe zone is. This is what it can handle this load. Okay. Next, the structural certification. The manufacturer also is structurally testing each of these pipes as they come off the machine. And as we run a certain amount of tests, we're testing one pipe per so many pipe manufactured to make sure that that batch is going to meet the necessary load. So we're giving that structural certification based on the requirements of the ASTM C76 spec. And so the manufacturer will provide you with the structural certification of that pipe to make sure it meets the loading requirements. Okay. When we look at what type of bedding or installation type we're using, that's going to be the responsibility of the engineer to call that out, to show the type of installation and what bedding and backfill material we need to be using, as well as the class of pipe. That is also the engineer's responsibility. Okay. Now, with flexible pipe, there's some things that the engineer needs to do. We need to come up with a trench detail, and that would be the responsibility of the engineer, because every installation and everything is different based on the soil types. Okay. You need to delineate the pipe zone. Now, typically, this would be 1 foot above the top of pipe, but it needs to be checked by the engineer. There's some calculations that are going to need to be done by the engineer to make sure that that 1 foot is adequate based on the loads and the different soils that you might be using here. Okay. The engineer is going to need to do a series of structural calculations that we'll talk about in a moment on what those are. And then the bedding and backfill material will also need to be specified and called out by the engineer to show what type of material they need to use and what the compaction requirements are to build that structural envelope. And then lastly, the engineer is also going to need to do some deflection calculations. Now, when I talk about the structural calculations, that could include, determining your in situ soils. It could be, it also includes designing the flexible pipe based on the in situ soils, or whether you're bringing in imported or borrowed materials, specialized soil to come in and structural backfill. To do that, you've got to determine your determine your compaction required for that structural capacity to make sure that the pipe doesn't deflect too much. You need to calculate your deflection based on your pipe and your soil. You need to determine your bedding requirements based on the field conditions that you're in. You need to determine your trench width based on the surrounding in situ soils. You also need to verify the depth of cover that's acceptable. And then you also need to check and make sure that that depth of cover is okay, not only for the strength of the pipe, but to counteract and counterbalance flotation So if you have any groundwater pushing up on that pipe, we need to make sure we have enough soil on top that's going to hold it in place to make sure that that flexible pipe doesn't float. So a lot of things going on there that we need to take a look at as a structural engineer. As you can see on the flexible pipe, we're taking on a lot more responsibility as the engineer because it is an engineered installation. So we need to make sure we're calling everything out. So why don't we start with the ASTM installation specifications? Let's look at that for both concrete and flexible pipe, and let's see what the differences are to see if there are any differences and what we need to do to make sure these things are going to be installed correctly, because that is the end goal. The end of the day, as the design engineer, we just want to make sure these things are being installed correctly. All right. So with concrete pipe, the ASTM spec is called C1479. This is the standard practice for installation of precast concrete sewer, storm drain, and culvert pipe using standard installations. So ASTM C1479 is the installation spec for concrete pipe. For flexible pipe, it's ASTM D2321. It's the standard practice for underground installation of thermoplastic pipe for sewers and other gravity flow applications. So we're going to be looking at C1479 for concrete and D2321 for flexible pipe. So as we get into there, we need to talk dirt. Let's talk dirty. All right. Now, keep in mind that we as engineers, we're kind of snobby with the language that we use. So we don't actually call it dirt. We call it soil. So instead of talking dirty, I think maybe we should talk soily. So I'm going to give you all a minute to recover from that hilarious joke. If you need more time, feel free to click pause on the video and until you've recovered enough to be able to go on with the presentation. I know that joke was absolutely hilarious. So take all the time you need, pause if you need to, but we're going to move on now. So let's talk soil. All right. So in C1479 for concrete pipe, we have these different categories of soil, and in flexible pipe, they call them soil classes. So you've got categories for concrete and classes for flexible. I'm hoping that I don't confuse you too much, but between that, the next thing is maybe gonna get even more convoluted and confusing. So bear with me here, stick with me. We can get through this together. Okay. So let's start with a category 1 soil for concrete pipe. Okay, if you notice, they have the USCS designations, but they also have the AASHTO M145 soil classification. Okay, that is, of course, your American Association of State Highway and Transportation Official soil groups that are very common in these types of specs and what we call out for these soil types. So a category 1 is going to be your clean, coarse-grained soils, your A1, A3 AASHTO soils. All right, so for concrete pipe, we're calling that a category 1 soil. Now, in flexible pipe, for that plastic, that thermoplastic spec, the D2321, they call it a class 2 soil. Same classification by AASHTO, same USCS description, okay? But in concrete, it's a category 1. In flexible pipe, it's a class 2. Okay. Now, for a category 2 soil for concrete pipe, these are your coarse grain soils with some fines, right? These are your A24, A25, A26, or your A4 and A6 soils with 30% or more material retained on the number 200 sieve, okay? However, for a flexible pipe, this is a class 3. So category 2 for concrete, class 3 for flexible. Same soil classifications, just one is category 2, flexible pipe is class 3, okay? Similarly, as we move on down the list, category 3 for concrete pipe is called class 4 in the flexible pipe, in the plastic spec. Okay, so these are your fine grain soils. These are kind of your more clay materials. These are the ones that have less than 30% retained on the number 200 sieve. So you're getting a lot more of that really fine material. These are A27s or your A4 and A6 with more than 30 or less than 30% retained on that 200 sieve. Okay. And then if you get down to a category 4, this is not recommended and not allowed for haunch or bedding. It's not a structure. It's a really bad material, expansive, collapsive soil. So you really don't want to use these types of soil for your installation. All right. And that's similar for the class 5. It's kind of the same classification of your A5 or your A7 soils. And so these are ones you want to stay away from when we're talking about installation and backfill material. Okay. Now, you may be asking yourself, well, what about the class 1 on the flexible pipe on that plastic spec? We're calling out a class 1 soil. What the heck is that? If a category 1 corresponds and relates to a class 2. What is this class 1 soil? Now, notice that in this table, there isn't even an AASHTO classification for this. There's not even a soil group for this. And the reason is because this is a very specific structural soil that you have to order special. Okay, I call it a super soil, right? This is a super soil that has the following characteristics. First of all, it's a crushed rock. It's angular. It has 100% passing the 1.5 inch sieve, less than or equal to 15% passing the number 4 sieve, less than or equal to 25% passing the 3/8 inch sieve, and less than or equal to 12 inch passing the number 200 sieve. So keep in mind, this is a very specific engineered structural backfill that you could use if you want to use that class 1. Okay. Now, because it's not an AASHTO material, it's not an AASHTO soil group, and it's not recognizing that, this is not very readily available. Okay. If you were to call a material provider and say, hey, this is the one I want, this is going to be a lot more expensive than your typical soils that you're going to find in your A1, A3s, your A24, A25, A26s, your A4s, your A6s. This is going to be much more expensive because it is a very specially designed soil. So keep that in mind, that yes, you can use this class 1. You can call it out as the engineer and say, we want you to use this class 1 soil because we can get better, we can get more fill on top of our pipe or whatever. But keep in mind, you're going to pay for it, right? It's going to cost you some money there. Okay. So sticking with that, with the soils and the types there, when we look at the category 1 on the left here from ASTM-C 1479, there's 4 different types of installation that we're going to look at. Okay. So if you notice type 1 through 4, type 1 is a very stout installation. You've got it talks about your bedding thickness, but then when you look at your haunch and your outer bedding, type 1 is a category 1. So your best A1, A3 material from AASHTO, compacted at 95% compaction. Right now, type 2 gives you a little bit of flexibility. Okay, you can have a category 1 soil, but you only have to compact it at 90%, or you can do a 95% compaction of a category 2. Right, so the installation and the bedding and the backfill material is not as stout as a type 1, which means we may have to increase the class of pipe so that the pipe is stronger, so that it can withstand those loads, because we're not transferring that onto the soil and the installation type, the bedding and the backfill there. Now, a type 3 is even more open-ended for the contractor, that it's not as strict an installation. You could use a category 1, but you only have to install it to 85% compaction. Category 2 is 90% compaction, and a category 3, so that lower quality material, compacted to 95%. A type 4 is kind of your lowest level installation. And you don't need any requirement for a class 1 or 2, or a category 1 or 2. But if you use a category 3, you only need to install it to 85% compaction. So again, the higher the type of installation, so a type 1, you're going to be able to get away with a lower class of pipe. But if you use a type 3 or 4 installation, you may have to increase the class of pipe there. So just something to keep in mind there. Now, on the D2321, this has some recommendations and restrictions based on the class 1. The next column would be class 2, the class 3, and class 4. So when you look at what restrictions are for some of these soils, it says that class 1 is acceptable where no migration is probable, or when combined with a geotextile filter media. So if you're going to use class 1 soil, that super soil, that really expensive stout soil type that isn't even classified in AASHTO, right? You can't use it if there's going to be a possible migration of fines. Well, where have you ever seen fines not migrating when there's groundwater or anything, right? So if there's any groundwater at all, you're going to have migration of fines. So you probably don't want to use that material according to this spec, unless you're going to wrap everything with a filter fabric or a geotextile filter or a drainage blanket or under drain. So something to keep in mind with that class 1 soil. Now, class 2, it says where hydraulic gradient exists, check the gradation to minimize migration. Again, they're concerned about soil migration. And the reason they're concerned about soil migration is because if any of those fines migrate out of that soil envelope there, right, we will undermine the strength of that backfill, and it could cause excessive deflection. So it's so important that we protect the integrity of that structural backfill on either side of the pipe, because if we undermine it, we could lose that structure. We don't have as much strength on the sides of the pipe, and so it's going to tend to deflect a little bit more. Okay, so we got to be careful with that. So these are just some recommendations and some restrictions that you have there that are available in D2321. So as engineers, we need to read through these and make sure that we're choosing the right soil type to ensure we've got that there. Okay. So when we talk about installation types, okay, there's two that I want to talk about. On the left-hand side of this, you can see this is a trench installation. On the right-hand side, this is an embankment. So when we look at trench versus embankment, I'll show you a picture here in a second on what the difference is. But keep in mind, when we look at these different areas on this standard trench detail here, as you notice right there, the middle of the pipe, that's your spring line. You've got your haunch area there. Underneath the spring line to the bottom of the pipe, you've got your bedding material underneath the pipe that's loosely placed and uncompacted so that the pipe can settle in and bed in there around it. So that's what we've got there. Now, the two different types of installations are trench and embankment. I want to point those out because this is important to note based on our fill height charts, and I'll show you that in a moment. So a trench detail or a trench installation, this is the most common installation type that we have, that we do in Utah. Most of what I see is trench, right? And this is basically, you've got the ground there, we dig our hole, we dig our trench, and then we put the pipe in and then we backfill. Now, the benefit of a trench installation is that because you've got the in-situ soils around the pipe, they're already in place, they're already compacted, they're already stable. Should be, hopefully they're stable there. But what it's going to do is, as we backfill, that trench wall is going to absorb and use some of that friction forces of the interaction between the new backfill and the existing trench. It's going to absorb some of that load, and that coefficient of friction is going to mean that we don't have as much of a load directly on top of the pipe as we would with an embankment installation. Now, this is a picture of an embankment installation, and this is the early stages of embankment. And what we do in an embankment installation is that the pipe is laid flat on the ground, so right on our foundation where we're at, and then we're going to build up around that. So as we build the road, we're going to build it in lifts around the pipe. Okay, so embankment installation, if we're calculating this in our class of pipe based on embankment, it's going to be more conservative because we don't have the coefficient of friction interacting with the new backfill that absorbs some of that load. So all of the load, 100% of the load in an embankment condition, if we're designing based on embankment, it's going to be right on the top of that pipe. So we got to keep in mind which type of installation we're looking at so that we can make sure that we're using it correctly. So again, we want to ask ourselves as the design engineer, what do I need to show on the plans to make sure it's installed correctly? So we already talked about some of the things we need to include, but let's go to the fill height charts, right? A great place to start, fill height charts. If we need to look at what the design is and what class of pipe we need, we talked about our installation type and our bedding that we need to use, and we also talked about the class of pipe. So let's go right into the fill height charts. So these are some fill height charts that are put out by the American Concrete Pipe Association. And I want to point out a couple of things about them. Number one, the notes and some of the assumptions, all right? These fill height tables are based on, first of all, a unit soil weight of 120 PCF, which is very commonly used in these types of calculations. It's also based on, number two, an AASHTO HL93 live load, which is what most DOTs and FHWA are using for highways and different road loading there. And the third one is the important one here. It's what we just talked about with our installation types. This is going to assume a positive projecting embankment condition, not a trench. So we're using the positive projection embankment. Okay, which means that this gives conservative results in comparison to trench conditions. So if I'm the engineer and I'm looking at this, I'm saying, okay, I'm going to look at what a type 3 bedding is, because that's going to give our contractor a lot more flexibility of what type of material he wants to use. So if he wants to use that A1, A3 material, that really good stout material, he can use that, but he only has to compact it to 85% for a type 3. If he wants to use that category 2 soil, he can compact it to a 90%. And if he wants to use a category 3, he has to compact it to 95, but it gives the contractor more options if we use a type 3 bedding. So that's what we're going to look at for here. So going back to our design problem, we need to look at a 48-inch pipe. Here we go, 48 inches. And we said that it's going to have 12 feet of cover. So if we go 48 inch on the left-hand side, that's our pipe inside diameter. And then if we look at our fill height along the top there, we go to 12 feet. And if we go where those two meet, and we draw our fingers down, if you notice, it goes there. It's that number 1300. But the more important thing is it's color-coded for us to make it easy, because some of us engineers need to make things, we need stuff really, really easy for us to look at. So this one makes it a lot easier for us because it's color-coded here. So if we look up to the top to the key, the legend here, this corresponds with a class 3 pipe. So we call out on the plans a type 3 bedding. We tell them what types of material they can use and what the compaction are. And newsflash, some municipalities already have that spelled out in their specs. So we can just piggyback on their specs and call it out and say it's a type 2 or a type 3 installation. Some of them might even be a type 1 installation. But anyways, we call out what type it is, and then we call out the class of pipe, class 3 pipe, class 3 RCP, and we are done. That's it for concrete pipe. Easy peasy lemon squeezy. We do our fill height table and we call it a day. We are done. All right. So let's look at the flexible pipe fill height charts here. This is a fill height table for flexible pipe. This is taken from one of the major manufacturers of flexible pipe of plastic pipe in the United States. I won't say which one, and I've removed any references to the company. But this is directly out of one of their technical notes and their drainage handbook. And so we can look at this together here. So here's our fill height table. Let's look at it here. So we go to our 48 inch here on the left-hand side there. This is our inside diameter in inches. Okay. So for a 48 inch pipe, if we look at that class 3 material, now keep in mind that corresponds to a category 2 material, right? That's a pretty good material there. If we compact it to 95%, we can get 12 feet. Okay, so that's 12 feet of fill. On top of that, at 95% of that class 3 or category 2 material. Okay. Now, if we look at a class 2 material, keep in mind that's that category 1 for concrete pipes, so the best material, that A1, A3 material, right? And if we compact that to 95% in the bedding and the haunches and on top through the pipe zone, there's telling us we can get 17 feet of fill on top of that. And if we look at that class 1 super soil that we've got engineered and we've got created for, especially for this project and delivered to the site, if we compact that to 95%, we can get that to 25 feet of fill. Now you're going to look at that and go, wow, that's pretty impressive that we can get that much fill on top of that flexible pipe. But wait, there's more. Let's look at a couple of these things here. First of all, their notes are somewhat telling here. We got to look at this. It says installation is assumed to be in accordance with ASTM D2321 and the installation section of the drainage handbook. Okay. Another one is this. This one's always interesting to me. Material must be adequately knifed into the haunch and in between corrugations. So what they mean by knifing is that the material needs to be compacted in between every single individual corrugation. And some of those corrugations are maybe only a few inches apart. So when you're looking at knifing into all those corrugations, the contractor has to make sure that he's getting that material adequately compacted in between each of those corrugations to be able to build that structural zone around the pipe. Okay. Compaction and backfill material is assumed uniform throughout the entire backfill zone. So that means if we've got material that's a little bit larger, we got to make sure that we get rid of that and it's all uniform so that it can go and compact smoothly around the pipe. Okay. Now, from the same company, they had a technical note that they released in 2016 related to the burial depths or the fill height tables for corrugated HDPE pipe. Okay. So what I want to point out on this technical note 2.01, it's pretty interesting to me. It says the information in this document is designed to provide answers to general cover height questions. Okay. Now, if I'm the design engineer and I'm looking at these fill height tables, I might make the mistake and assume that those fill height tables are intended to be used for design. However, the rest of that sentence explains that that is not the case. The data provided is not, I repeat, is not intended to be used for project design. The design procedure described in structures section 2 of the drainage handbook provides detailed information for analyzing most common installation conditions. And this procedure should be utilized for project specific design. So if I'm that design engineer and I'm calling out the manufacturer's recommendations, right? This is what they're telling me. I need to, as the design engineer, not use these tables. These are for reference only and just to answer my general questions. Because I'll tell you what, there's many times when I'm sitting around with some buddies and we're talking and we're just shooting the breeze, when the question comes up as a general cover height questions for thermoplastic pipe. And so if that's the case, if you're just shooting the breeze with some buddies and you want to talk about these cover height questions, feel free to use this fill height table. But if you're going to use it for design, for this project-specific design, you need to go through section 2 of the drainage handbook and go through their structural calculation section there. Okay, so don't use this. Don't make the mistake and use that. Now, something else that's really interesting is this is from the technical note 2.01 that was dated October 2016. There was another one that came out in 2008. And what I want to point out is that they're not consistent. They're not the same. So make sure you're using the most up-to-date technical note and information from the manufacturer. So if you have an old one, make sure you go and get the most recent one. And the reason I say that is because of this. Okay. If you look at a 48-inch pipe from the one released back in 2018, the class 3 at 95% compaction says we can get 14 feet of cover. But the one in 2016 says 12 feet. So it's decreased by 2 feet on that one. For a class 2 pipe at 95% compaction, it said 20 feet of cover. The 2016, the more recent one, was reduced to 17 feet of cover. And the other interesting thing is if we're looking at 12 feet of cover, in 2008, you might have said that a class 2 at 90% compaction will give us 13 feet of cover, and we're fine to use that. But the one in 2016 now says it's only gets you 11 feet of cover, so you need to do a better installation there. Class 1 in 2008 was at 30 feet, and Class 1 in 2016 reduced to 25 feet. So there are some changes and some things that happen there. So keep that in mind. But we know that this is just for our casual conversations with our buddies, and it can't be used in project-specific design. So we better do what the manufacturer recommends, follow their recommendations, and look at section 2 structures, okay, of the drainage handbook. Now, I want to point out that this section, I've read it, I've worked through it, I know how to do it. This is a 25-page document, and there are 21 specific equations that you need to use and go through to do these calculations adequately for every project you do for flexible pipe. Now, this is the note at the bottom of section 2 of the drainage handbook of this manufacturer. The buyer or user, so that would be your contractor or your municipality that's the end user of that product, is responsible for serviceability of the product in any given application. The seller, so the manufacturer that's selling us the pipe, is not responsible for injury or damage resulting from improper installation, non-compliance with these guidelines for installation of product, or use outside the guidelines set forth there herein. So this is the disclaimer. This is the shifting of liability and responsibility should anything go wrong if you do not follow this section of the drainage handbook step by step and you don't go through these calculations. This is where the manufacturer says we are disavowing all knowledge of this if you don't do it correctly, if you don't go through the proper design. So keep that in mind, that that falls solely on the end user and their engineer to make sure it's designed and installed correctly. Here's another note on the introduction there. The information in subsequent areas of this section provides step-by-step guide for the structural design of non-pressure corrugated polyethylene and polypropylene pipe. The methodology is based on the AASHTO design procedure and has been proven through test installations and actual projects to be highly conservative. Okay. More discussion on actual installations is included in section 2-5. But we're focused mostly on design because we are the design engineers, so we're going to look through this, and we're going to go through this step by step. So the first thing that we need to do, according to section 2 of this, is we need to go through and calculate all of our loads. So first of all, we mentioned that we had dead loads. Those would be your soil loads that are on top of that pipe, right? We also have the hydrostatic loads. Those are the surcharge loads that we're talking about, the loads where you've got water pressure either on top or below the pipe. That's also going to have your buoyancy forces. So there's always going to be these loads that are putting pressure on this pipe. So you have to go through and calculate those loads first. Once we know the loads, we can use those loads to calculate wall thrust. Now, there's different wall thrusts that we need to calculate. There's first short-term thrust, as you see in equation 2-6. There's the long-term thrust, combined thrust. But then you also need to calculate in equation 2-9 tensile resistance to thrust and your compressive resistance to thrust. So a lot of thrusting going on here. And those equations don't look super fun. Not the most fun thrusting equations you can have. So moving on. Okay, this is an interesting thing as well, because you have, if you notice on the left-hand side there, you've got a typical corrugation profile, right? That's a little bit rounded and curvy and that, but that's hard to use calculations on curves and things. You're going to have to integrate and use calculus and different things to solve those exactly. So what you need to do is you need to choose based on the corrugation profile that you have based on that pipe. So you're going to have to find from the manufacturer what that corrugation profile looks like, and you have to apply it to an idealized corrugation profile, or one that is basically straight lines and sharp corners and good angles that you can measure and calculate and use that. And what you're going to do is you're going to take that idealized corrugation profile and you're going to apply it to calculate the effective area of that corrugation. So once you have the effective area, you can use the effective area to calculate your stresses and your strains. Okay, so if you see that AEFF, that's your effective area that's used according to that idealized corrugation profile. So once you have the idealized corrugation profile and the effective area of that, you can use it to calculate your critical buckling stress, your factored compressive strain, your pipe deflection due to bending, and your factored bending strain. Now, you can also use all of those strains to calculate these last four equations, your factored combined compressive strain, your limiting combined compressive strain, your factored combined tension strain, and your limiting combined tension strain. These are the 21 equations that you need to use to go through section 2 of the structural hem. And I know we went through those fast and we didn't work through all of them, but you as the design engineer must go through each of these calculations and do these to ensure that that everything that you're calling out and the way that you're designing this is accurate, because we can't just use those fill height charts for flexible pipe like we can with concrete pipe. We have to go through and calculate to ensure that we're doing it correctly, or else we're taking on all the liability on ourselves, as it points out in all those disclaimer notes. Okay, so for flexible pipe, it requires the calculation of, first, we talked about wall thrust, short-term and long-term, right? That's very important. Determine your idealized cross-sectional area, your effective area there, to calculate buckling by determination of critical buckling pressure, your bending by determination of the bending strain and the bending stresses, and your compression and tension strains. So that's what we have to calculate first. But the next step is probably the most critical of all of the calculations that we need to do. And that is because our pipe acceptability at the end of the project is based upon our deflection. As we pointed out before, flexible pipe wants to deflect. It wants to squish a little bit. And so in order to counterbalance that, we need to make sure that our soil and our loading and our compaction and everything we're doing to install that is well within our minimum deflection requirements. Okay. So then the last and probably the most important calculation we have to do as the design engineer is our deflection calculation using the modified Iowa formula. All right, so let's talk about the modified Iowa formula. Great formula. As far as formulas goes, this one is at the top of the list. It's a great formula. Pythagorean's theorem formula, that's a great formula too. But this modified Iowa, I'm about to blow your socks off here with this. It's great. All right, so let's look at it. Deflection. This is all about deflection, and it's basically, when we think about deflection, we're looking at the percentage of deflection and how much that pipe's going to squish or change in the y-axis, so up and down, and it's based upon our load, and it's our ability to withstand that load with two things. Number one, our pipe stiffness, and the second is our soil stiffness. So the combined pipe and soil structural capacity need to withstand enough of that load to keep our deflection low enough so that we can meet the deflection requirements of 5% or less for thermoplastic pipes. Okay, so this is the equation, how it looks right on the top there. Those are loads. Remember, we talked about our live loads, our combined loads. We have to, or our dead loads. We have to look at our construction loads. We have to look at our surcharge loads. So the top there is all of our combined loads. And then on the bottom, we've got on the left-hand side of that plus sign, you've got your pipe stiffness, which is your 0.149, which is your constant times the pipe stiffness coefficient. And then on the right-hand side of that plus sign on the bottom there on the denominator is our 0.061, which is our constant, times our E prime. Now that E prime is what's called the horizontal modulus of soil reaction, okay? And you'll say, wow, Jason, that's awesome. Horizontal modulus of soil reaction, that sounds exciting. Where can I find that? And I'm like, it's from a table. Find it from a table. So for 48-inch HDPE with 12 feet of cover, we're going to look at, for this one, an H25 live load, okay? For that, we have a PS, or our pipe stiffness, of 18 PSI, and our E prime, or our horizontal modulus of soil reaction, is 1,000 PSI. Okay, so all good and well. Everything looks fine there, okay? However, when I look at this, I kind of start thinking to myself, you know what? That 18 PSI and that 1,000 PSI, those are pretty critical numbers, right? When I substitute those in, and I calculate it out and I multiply everything out, this is what I come up with right here. 2.682 plus 61. And when I add those together, and if I were to take the ratio of what each of those values on that denominator are, and keep in mind, this is the ability to withstand the load under a certain amount of deflection, right? The pipe portion of that only accounts for 4% of that number, while the soil accounts for 96% of that. 96% is related to the soil. And what's even more interesting is that horizontal modulus of soil reaction, like I said earlier, that's pulled from a table. It's empirical data that's pulled from a table. And I'll be honest with you, I'm not 100% sure how to come up with that and how to calculate it, right? Now, one of my favorite people when I was growing up and I used to love to watch on TV was Bill Nye the Science Guy. Bill Nye the Science Guy used to always say, it's not magic, it's science. And I always love that because some people, you know, they look at things and we think, oh, that's magic. How they do? No. This is science. So let's talk about the science. Okay. When we're dealing with steel, okay, if I'm an engineer and I'm manufacturing something and I'm manufacturing it with steel, right? I know that the yield strength of steel is 36 kips per square inch, or 36 KSI. How do I know that? Because I get a mill certification from the manufacturer, from my supplier, that tells me it's been tested and checked to be 36 KSI. Perfect. If I'm designing with concrete, okay, I know that the compressive strength of concrete is 4,000 PSI. And how do I know that? Well, because I'm able to test it. I can take a test cylinder and I can go and do a 7-day or a 14-day or a 28-day break in my quality control lab, and I can determine that that concrete either meets or exceeds the 4,000 PSI compressive strength. Boom, done. I can test it. Now, when I'm designing with soil, if I look at that modulus of soil reaction there, the horizontal modulus of soil reaction, and I say the E prime is 1,000 PSI, I mean, it should be science, but it's often magic. And what I mean by that is that if the soil was tested, if we went out and tested that soil to determine what that E prime value was, then it's science. But if we're not out there testing it and making sure and verifying that that number, that E prime of 1,000 PSI, is correct and accurate in our calculations, then some might argue that that's just magic. Maybe it's not science after all. Okay. So what's interesting is when we look at this table and we look at the different diameters of pipe and we compare, based on that modified Iowa formula, what the pipe contribution is to the total structural capacity of the pipe envelope versus the soil contribution, you notice that at a 48-inch pipe, 4% of the structural capacity comes from the pipe itself, while 96% comes from the soil. For smaller diameters, like a 12-inch diameter pipe, it's a little bit higher, which would be expected because there's, you know, the pipe itself is a little bit stiffer because the corrugations are bigger in relation to the pipe itself. So you're going to see 11% pipe contribution versus 89% soil contribution. But when you get down to the larger diameters, even your 60-inch, you're looking at 3% of the structural capacity of that pipe system to be the conduit and the structure. The pipe is only contributing 3%, while the soil contributes 97%. The interesting thing is with rigid pipe or concrete pipe, whether you're using reinforced or non-reinforced concrete pipe or clay pipe, for rigid pipe, it's actually backwards. The pipe itself is withstanding and taking sometimes between, depending on the class of pipe and depending on the insulation type, it could be anywhere from 85 to 95% of the structural capacity is borne by the pipe itself in concrete, and only 5 to 15% is being borne by the bedding and the backfill and the load around it. Okay. But in flexible pipe, it's different, especially in thermoplastic pipe here. So for the larger diameter pipe, you're putting a lot of faith and a lot of trust as a design engineer in the contractor's ability to install it correctly and build that structure around the pipe to keep it from deflecting. So when we look at deflection, if we keep that table and we update it for 5% deflection on how much that is, keep in mind that for a 48-inch pipe of what we're talking about, the allowable deflection of 5% is only 2.4 inches in the Y direction. So that pipe can only shrink 2.4 inches. That's pretty small, right? That's not much movement. So we are, like I say, that E prime number is doing a lot of heavy lifting in these calculations to ensure that our soil is compacted and put in place and installed correctly by the contractor to ensure that we can meet this 5% deflection number. Because the last thing we want is for a contractor to have to come in and rip up a road and remove a pipe because it exceeded 5% deflection. Nobody wants that. It's not good for the end user. It's not good for the traveling public. It's not good for the contractor. It's not good for the engineer. So we need to make sure that we're designing this correctly. We're going through all of these necessary calculations to ensure that our soil structure is built correctly. Okay. So when we look at these specs, okay, this is what I'm hoping we take away from this. And if we look at concrete pipe, if I'm a design engineer, I'm going to tell the manufacturer to manufacture this pipe per ASTM C76. Every local spec I've read, here in Utah and Idaho, they all call out ASTM C76. And they're going to say install per ASTM C1479. And the manufacturer of the pipe is going to say, fine, we already do that. That's fine. We're good to go. C76, everything meets it. We've tested it. We're good to go. Certified. Boom. Structurally complete. You're good to go. Installer is going to say, fine, ASTM C1479, perfect. You got the trench detail. You've got all the bedding types and materials and things that we want to use. Great. We're going to use this type of material. We're going to bed it here. Great. Wonderful. Boom. Engineer calls out the class of pipe, puts it on the plans. Bob's your uncle and everything's good. Now, the flexible pipe is a little bit more convoluted and different because the engineer, what we like to do is we like to say as per manufacturer's recommendation. That's a way that we as engineers, this is kind of a little pro tip that for those of you that are non-engineers, I don't want to, show you too much behind the curtain here to see the wizard back here. But we tend to put things like as per manufacturer's recommendations on our plans a lot. And what that does is in our minds, that relieves us of the liability because we're telling you to build it as the manufacturer's recommendations. Which in concrete pipe, if you look on the left-hand side, that's fine because the manufacturer's recommendations are all clearly stated and we're good to go. But when we look at what the manufacturer's recommendations are, as we have with the Section 2 drainage handbook, it often says manufactured or installed as per ASTM D2321. So manufacturer's telling us to install it as per ASTM D2321. So you as the design engineer say, that's fine. We still have the onus of responsibility on the installer for ASTM to install it per ASTM D2321. However, this is where things get really, really interesting. In ASTM D2321, the engineer's responsibility is referenced 29 times. 29 times this spec calls out what the engineer needs to do, what the engineer's responsibility is to include in the plans and the specifications to ensure that this pipe is installed correctly. So it effectively sends the liability right back to the engineer. So if we're just calling out manufacturer's recommendations and not doing all of the recommended calculations per the manufacturer's drainage handbook and per ASTM D2321, then the liability falls back on us, the design engineer. So let's look back at our hypothetical situation from the beginning of the presentation. Construction drawing, call out 48-inch RCP. Contractor wants to use 48-inch HDPE because his brother-in-law is the plastic pipe sales rep, and he can get a good commission on this sell. The contractor plans to install the HDPE exactly as shown in the plans, which is designed for RCP. You're the design engineer. Do you approve the change as is? I'm hoping that by now, after this hour, you are saying absolutely not. Consider this. If the HDPE fails, if that pipe system, that 48-inch pipe fails, because it is substituted for RCP with no changes to the plans to include specific installation details based on the manufacturer recommended calculations, who is liable? Who is responsible to cover the cost of that failure? It's the engineer, the design engineer. So if you're going to accept that and you're going to allow a contractor to substitute a flexible pipe for a rigid pipe, be ready to bear the responsibility should that pipe fail. So there's a few key takeaways that I'm hoping we take from this presentation. Number one, rigid and flexible pipe are different. The materials are different. The functions are different. While rigid pipe is a conduit and a structure, flexible pipe is just a conduit. When you buy rigid pipe, you're buying the structure that accompanies the whole. For flexible pipe, all you're buying is the whole. It's your responsibility to build the whole, which takes us into number two takeaway. Flexible pipe cannot be installed the same as rigid pipe. It cannot happen simply because flexible pipe is a liner. As I said before, you are buying the whole. It is your responsibility to build the structure. And the third and probably the most important takeaway for my engineering friends, and something that I didn't learn until I started researching this and reading these specs and learning more about the differences between rigid and flexible pipe, is this. And I'm hoping this sticks with you and that it helps you at some point in your career to protect you. The engineer, the design engineer, you are the engineer, take on the liability for structural design and installation of flexible pipe. While using rigid pipe and concrete pipe, the plant is going to certify the structure, but in flexible pipe, because it's only a liner and you need to make sure that it's an engineered installation and that it's installed correctly, you as the design engineer have the onus and responsibility to ensure that it is designed structurally and correctly, and it is installed per your design. For more information about this topic or any of the Oldcastle products discussed in this presentation, please feel free to email me at jason.allen@oldcastle.com or feel free to visit oldcastleinfrastructure.com.